seeing more and more on physics today and tomorrow. Especially today will be about electromagnetic physics. In the first lecture, when we were talking about physics, we were talking about the physics list. Just to remind you, this is the place where you define your physics environment, you create physics processes, particles, and you assign them. Now, later on, in the second lecture, we saw a bit about processes. In general, the physics processes, what information a physics process need to provide during the simulation. Now we go even one step deeper, and we will see, especially in case of electromagnetic, how a process is built up, for example, from models, and what models are available in different parts of the electromagnetic, what physics constructors are provided by Geant4. If you remember, these physics constructors are the building block that you can take as it is, plug it into your physics list and use, and you can change with one line whether you want to use more accurate but a bit slower, or fast but less accurate a combination of physics, and you will see all these things today. So in the first lecture, I will show the structure of the electromagnetic physics in Geant4. And you will see that one part of this electromagnetic physics is called the standard electromagnetic physics, that we will see in this lecture a bit deeper. Okay, and we will see a few specific things in this electromagnetic physics, but just after we saw what kind of prepared electromagnetic part of the physics list, electromagnetic physics constructors, are provided by the toolkit. So let's see how the electromagnetic physics directory looks like. So first of all, you can find exactly the same structure if you go into your Geant4 source to processes electromagnetic. You will find something called standard. It contains models and processes to describe, of course, electron-positron and gamma interactions up to very high energies. Also, electromagnetic interactions of hadrons and ions. These are, under this directory, you will find the models that usually contains a bit stronger approximations, okay, in the description of the interactions, which means that the model these models are usually a bit simpler, okay, but it makes them faster. They do not really care about what happens if the gamma has very low, or if the electron has a very low energy. Okay, at lower energies they become less and less accurate, but they are very fast. So standard means actually in the electromagnetic that it focused on more on medium and high energy applications. Now you also find something, a special directory to describe muon interactions, but you can see here the low energy part of the electromagnetic. Practically you can find all the interactions here in the low energy part for gamma electron positrons. Some of them are quite similar here, but usually what we can say, what you can find here, the theoretical basis of the models that you can find in the low energy part will contain less approximation and will be more precise, including more details on the atomic structures. Okay, here models will sample, for example, atomic shell for an interaction and so on. Here we do not really care. Okay, we describe some effective way all these details. On the same time, I must mention already here that there are models developed in the standard electromagnetic that are happily used in the low energy part, because they are more accurate than they could do here. Okay. And of course, you will see that it's the same, that here we are using something for here. And how is it possible? You will see later. I was talking briefly yesterday about X-rays like Cherenkov, transition radiation, and so on. These interactions are sitting in a separate subdirectory. Also, there are a set of polarized models, and I will talk about the DNA physics in the next lecture together with the low-energy electromagnetic, a bit more details, so you will see this part. One important subdirectory called utilities. Here you can find all the base classes. Okay, that's special for the electromagnetic part of the toolkit. So, what are here? You will see a bit more. So, in this lecture, we will focus actually on this part and a bit here in the utilities. Yes. About? Well, reverse Monte Carlo, it's a special simulation technique that you can, under some condition, you can start a simulation not from your source but from your target. Okay, it's true. It's a fast way of simulating things. It's true if your target, if your primaries are coming isotropically to your target. Okay. Then in this way you can make tricks. You can start simulations from both sides and you can make some association. There are something, even reverse Monte Carlo, used in, for example, low energy electron transport simulation, where you usually have an electron gun. You have your target and an electron spectrometer where you measure electron backscatter, electron energy, angular distribution, and so on. And you imagine that these detectors has some acceptance angle. That's just a small part of the space. So if you start to simulate, hit your target, many of the simulation at the end that comes back electron, you spend lots of energy and time, but they simply won't be detected because they don't lie into the acceptance. So you need to do billions of simulation to get some statistics. Okay, and there are techniques there that you start some trajectories in a reverse mode from your detector and from your gun. And under some conditions, you can make some associations. So you can get a good statistic instead of running for a few days, few seconds. Okay, but some conditions need to fulfill. So, what is inside the standard and what we will try to see today are more on photon interactions, conversion to electron-positron pairs, incoherent and coherent scattering of the photon, and photoelectric effect. And as I mentioned, there is a photo-induced nuclear reactions. They are sitting in the hadronic part, not here. I mentioned here just the completeness. For electrons and positrons, there is ionization, Coulomb scattering, which is elastic scattering, Bremsstrahlung photon emission, positron annihilation, in case of positrons, of course, and of course there is this leptonuclear interactions similar to the gamma nuclear one that are sitting in the hadronic part. So, when you were running the example yesterday and before, usually the verbosity, which means how dense the printout, okay, in these examples are set in such a way that you see many information before the simulation starts. And at the beginning you will see many information regarding your physics list. And if you go and start to read and you would like to understand how you read this information, then just come back here. And I said that for photons, the electromagnetic interactions are conversion, Compton scattering, photoelectric, and coherent scattering. And if you see, for gamma particle, there is photoelectric, for gamma particle, Compton scattering, for gamma particle, conversion, for gamma particle, the coherent scattering. You can see, and if you go further, you will see for electron, the list, and for positron and all the other particles. particles that you defined in your physics list, okay, the construct particle part, or defined in the physics list that you took from the toolkit, and you will see the list of processes that are assigned to that particle in that physics list. Okay, if you choose the physics list, you might see something else here. Okay, so it's good when you have the printout, you can go there and you can check if everything is assigned and works in the way in which you imagined. Within the electromagnetic subpart of the toolkit, there is one very good thing that I will also mention in the low energy part, is that there is a coherent design, which means that the model and process descriptions and so on, they are follow the same interface. Okay, for the low energy and the standard. It means you will see there are many good consequences. So, as I mentioned yesterday, that the interactions are described by processes. Okay, the G4V process was the main interface for describing each process. And you can see G4 Compton scattering is a process to describe Compton scattering of the photons. As I mentioned yesterday, such processes are assigned to the particles in the physics list. Now, within the electromagnetic framework, if you want, there are 3 special processes, which means that the electromagnetic processes are not finally this G4 Compton scattering. It's not directly implementing the G4V process. There are some intermediate specification before them. Okay, we have some special interfaces for describing electromagnetic processes, kind of simplified, tailored to describing electromagnetic interactions. But there are some special types of electromagnetic interactions. This G4V-EM process describes pure discrete interactions, like this Compton scattering of the photons. Okay, which means that all the other, the continuous at-rest part, we do not need to care. Okay, so it's simplified, already done. We need to implement, because all the photon interactions will be discrete. Now, we saw yesterday that ionization and Bremsstrahlung is described as continuous discrete interaction. Ionization and Bremsstrahlung need to provide a restricted DEDX, restricted cross-section, so they are different than the pure discrete interactions. So for them, there is G4V energy loss process, that is a continuous discrete process, providing interface to implement your way of computing restricted DEDX. So back to your question. Before yesterday, I think, or yesterday, you take a G4V energy loss process as a base class, you derive your own ionization process, and you implement here how you want to compute the DEDX. Even better, you go the already available G4 ionization process, and you derive your class from that. And you just overwrite the DEDX computation part. Then all the sampling of the final state, everything will be used from the class above. Then you take your process and replace in the physics list the ionization process with yours. Then you run the simulation and everything will be accounted that you put there. 5 minutes, depending on how complicated to implement your DEDX. Okay, so this is the point. Now, we will see today few times that Multi-Percolon Scattering is a tricky way to describe Coulomb scattering, but we need to use it. We will see why and how. But there are special information that this process needs to provide. So there are special information channels needed for this process. So this is why in the electromagnetic there are a special interface to implement multiple Coulomb scattering interaction. This is this G4 multiple scattering process. Now, an important thing is to see that so far I was talking about processes. Okay. But in the electromagnetic, you can think about processes like some kind of frames, okay, that you need to feel. Because process itself do not contain anything about the description of the interaction. Process will be a container for some models, electromagnetic models. And electromagnetic models will implement some theoretical description based on differential cross-section, whatever, of the given interaction. And for the electromagnetic models, there is, I don't know if I write it or not, okay, there is a base class for electromagnetic models, and actually, eventually, through the process, it will be the model what handles the interaction, which means it will be the model through the process, one or two, that will answer all the questions that the process needs to answer. So if the process is asked, give me the interaction length, then the process will look for the proper model that is inside the process, and will ask the model to give me this information. Okay. The process itself usually is an empty story. No. When you have already a G4 Compton scattering process, then it means that the developers already created a process and already added some model to this process. Regarding the naming, if you see something like G4 Klein-Compton model, you can see that the first part refers to the model name, and the second part refers to the process name, the interaction that the model describes. In this case, Klein-Compton model, this is one of our Compton scattering model based on the Klein differential cross-section to describe Compton scattering. You saw already this Klein differential cross-section. In the first lecture, Dennis was showing this differential cross-section, for example. But the important thing here is the naming convention, okay? So from this, you can see immediately what's going on. And as I mentioned, there is an interface to implement electromagnetic models, G4V EM model. And this will answer what is the cross-section and what is the final state. So when I'm saying that a process builds up from models, you can imagine the following. If you come here and you see actually these things when you have the printout, and we go one step further, you can see that, for example, the gamma conversion process, here the process, the interaction is conversion of gamma into electron-positron pairs. Now, what models are in this process? In this case, there is a model called Bethe-Heitler model that will be used if the gamma energy is between 0 and 80 GeV. And there is a second model called Bethe-Heitler LPM that is used between 80 GeV and 100 TeV. So you can see that a model can describe an interaction in a given energy range, for example. Then you can combine different description of the same interaction. You can combine in this way, for example, in this second model there is a special effect that is included, okay, that happens only at very high energies. Computing that effect is really time consuming. At low energies, below actually 100 GeV, you don't see anything from this, okay? So why you would compute even at low energies this tons of unnecessary thing? So you are using a simpler model. So now you see the power. You can combine different models based on different level of details of description into the same process. And when you run your simulation, you will see all this information printed out. And you can see that other model, like the photoelectric effect, is described by only one model, the Livermore photoelectric model. Any question regarding this? Yes? This case, yes. 80 GeV. Yes. Well, first of all, there is no difference. You will take the lower one. You will take the lower one because you start and you will check the first one that will fulfill the condition of being the energy in the proper range. But in this way, in this case, and usually what's happening is that the models has much more overlapping than a single energy point. These two models are giving exactly the same answer in a wide energy range. Yes, in the electromagnetic, what you need to do is that when you assign a model, you need to tell the low and high energy that you want to use this model. And this must be ordered in a continuous way, like this. Okay, it cannot be that you leave a gap. Frankly, we are taking care if you leave a gap, but then you don't know. I know what will happen because we will correct your mistake. But don't do that because you want to know what you are doing. So don't give a gap and don't make overlaps. No, it will be different in the hadronic physics, for example. But Dennis will talk about it. But in the electromagnetic, you want a full coverage without any gaps and any overlaps. Okay, and they will be nicely continuous, the cross sections and everything. Even if there would be some step, we make sure that it's not a step like this. Okay, there is a continuous transition. Other questions regarding this part? Okay. Let's move to the physics constructors. You can see many things on this slide, but the important thing is what I want to show is what are those predefined electromagnetic physics constructors that I called some modules, physics modules, that you can take and use in your physics list. And I showed in the physics list that you can switch easily between these electromagnetic options in your physics list. So everything that I describe here, we already discussed at the physics list. So I repeat here just to complete this constructor part. So first, let's see those electromagnetic constructors, just to remind quickly that these electromagnetic constructors will contain the electromagnetic part of your physics list, including the definition of the particles, creating processes, and assigning processes to those particles. First, three constructors, electromagnetic constructors, that will use the standard electromagnetic physics. Okay, that category, nothing else. No, these constructors, the default one, that we call default, okay, there is no default, but this is the basic, okay. EM option 0, or if there is nothing at the end of the physics list name, then this will be taken, okay. If you write explicitly EM option 0, it's the same if you don't write anything. And this will be G4 AM standard physics. Now, each of these electromagnetic constructors are used by someone. There is a user group who are using these constructors. It's not that we invented one and we thought it will be good for something. No, there are users. And in this case, actually, Atlas and some other HAP experiments are using this electromagnetic set of processes, models, and settings. And This, as I mentioned, the standard electromagnetic constructors will be good at high energies, intermediate energies, less and less accurate if you are going to lower and lower energies. We can do even worse if you want. We can do much better if you want, you will see. So it's a good compromise between speed and accuracy. Now, a bit of modification of this physics list, electromagnetic physics list settings, actually changing a bit the multi-Coulomb scattering stepping algorithm. We are even less strict than here. And we apply production cuts. I told you that production threshold for electrons, for example, applied only in ionization by default, but there are gamma interactions like Compton scattering that producing electrons as well. So with the flag, you can apply the production threshold also on those secondary electrons to create low energy secondary electrons coming from gamma. And this is turned on in this physics list. And we call it option 1. And this will be actually significantly faster than this one. But since the multiple, we will see what is multiple scattering a few times today. Okay, at the end, hopefully you will see why actually this choice, this difference. That the multiple scattering step limit is less strict. And it will work very well, this one, if you have big crystals where you don't have a very fine-grained detector geometry. But this one won't work. I mean, will work, but will give you quite wrong result of the stepping if you have a fine-grained detector structure. Okay, and this is why this is used by the CMS, actually, because they have big crystals, while Atlas has more detailed geometry, so they use these things. Okay, it will be much, much faster. But you need to be careful to take this one. And it's not the fastest, because there is even faster, where we even don't do the whole multiple scattering duties. Okay, we don't compute something in multiple scattering because it's even, they don't care. Now, this, if you take this physics list and you do some middle energy electromagnetic physics simulation in detailed geometry, the result that you will get could be hardly further from your experiment. Okay. So you need to be careful. These are special physics. This is special physics list used by LHCb. This is very good for them, okay, because they don't care about many things, because they will get a relatively good accuracy for them. But each of them, you can see, even the high energy Atlas, CMS, and LHCb are using 3 different settings. So you, as a user, you will use a 4th and 5th and 6th and so on and so on. Probably not this, actually. So let's move one step further and see a bit more accurate description of the physics. It's even not bit, but more accurate description of the electromagnetic physics, where actually the physics models and processes are combined, which means combined standard and low energy. So some processes and models are taken from the low energy part. So in this physics list, actually in option 3 and option 4, and also through here, but in option EM standard physics, so you see that the base is still the standard models, but in the processes, we plug in at the low energy part models coming from the low energy description that are more accurate. So in this way, the processes in this physics list will work fine at high energy, and when you go down to lower energy, then it will work fine because we have a model at the low energy part that's more accurate at low energy than the original standard. So this option 3, the difference between option 3 and option 4 is that option 3, I would say it's a fairly accurate description. still using the urban model for electron-positron multiple scattering. Don't care about what is it, you will see. But option 4 is the electromagnetic settings, the physics model settings, and all the parameters, stepping and so on, that we can do the best today in the electromagnetic description. Okay. If you find disagreement between your experiment and simulation using EM option 4, then please immediately report it. So, option 4 will use a really accurate description, for example, this multi-Percolon scattering. But if we move further in the low energy in the next physics lecture, you will see more on this Livermore physics models and this Penelope physics models. These are alternative set, for example, for low energy electron gamma and electron positron gamma interactions. We will see in the next lecture. Now, if we go even further, there is a set of constructors that are available in the toolkit, but these constructors are used more by us developers for validation of some physics models. Okay, so you can take it as a user. For example, this EM standard Wenzel VI, and you can use, you can change, and you can use in your application because it's available in the toolkit. But the primary reason why it's there, it's more for the development and validation of some models. Because the difference actually between these three models, the main difference is you can see from the ending how the Coulomb scattering, electron-positron Coulomb scattering, actually only below 100 MeV is described. That's the main difference. Here it will be the Goldsmith-Sanderson multiple scattering model. Here it will be the Wenzel VI, which is a mixed simulation model, and here it will be a single scattering model. But that makes a huge difference, okay? Because between this and this, there is, I think, at least a factor of 10, 15 in speed, and between this and this, there can be a factor of 100 or 1,000. While they give the same result. So, before we move and see a few special things, I repeat again, and I will do it later again and Friday again, regarding the physics list, because these constructors will be that you will use in your simulation. Or actually, this is what we recommend, that you start your simulation with one of these electromagnetic constructors, that the developers who knows very well the details of the different processes and models were put together for some application areas, targeting precision or intermediate precision speed or really fast speed. According to your need, now you can come even to this presentation, you go and you pick up what is your starting point. This is the easy way to go, to start to validate your physics. You pick up and you will start to check if it's good for you or not. You start to change here and there. But as you could see on Monday, you can do your physics list by yourself, but this is a bit more complicated and you have much more a chance to make mistakes. And of course here the description is that, as you could see, each physics constructor is targeting some application areas. And you can find your application area, you can choose your physics constructors. Any questions regarding the constructors? And I showed in the physics list lecture at the end that it's very easy to change between EM option 0, 3, 4. You just need to change the end of the string of your physics list if you use the physics list app. Okay. Now, let's see if you... okay, this might be useful if you want to see some quantities like what is the stopping power for electrons in lead used in the simulation in a given physics list, then there is something called EM calculator, and here I show a piece of code that you can do, but actually I would recommend to go to this test EM0, which is an example, and in this, if you build this example, and if you run the macro, you can set what is your target material, what is your target, what is your primary particle, what is the energy, and if you run, it won't be a simulation, okay? But what will happen that in this application, your physics list will be checked. For this particle, all the processes will be asked to compute quantities like cross-section, stopping power, whatever, in the given material that you set, at a given energy that you set, and it will be nicely printed out, all this information. So if you would like to see what are the quantities used when you are using a simulation, because you would like to compare with some others, for example, then you can use this application to extract practically all the cross-section, stopping power, range information from the electromagnetic part. So few special topics, just in a nutshell, okay? Some of these will be discussed in much more details later on after lunch. Actually, this one as well, I will show in the DNA part, even a movie that will be nicer than this. The point here is that imagine this situation where you have a relatively big detector, and here in this very small part of your detector, you would like to use a very detailed, very precise description of the physics. Practically here you would like to use actually EM option 4 description. That's the most accurate. Or even like here, DNA, you will see what is this. But on a big part of your detector, if you would use that precise description everywhere, that it would consume too much time, because of all the precision and so on, that you cannot afford. No, in the electromagnetic, you can combine different models per region. So Makoto mentioned that if you have a detector, you can define detector regions. And in this case, this part of the detector and this part of the detector belongs to region A, you can see, and this small part of the detector belongs to region B. And in the electromagnetic physics, in your constructor, actually you can set models to be used, for example, for describing Coulomb scattering in a given region. And in other regions, something else, as you want, will be used. So in this way, you can get the best speed and accuracy combination. Okay. Now you can do it even with special user commands. You will see in the next lecture in the DNA, when it's combined with DNA, what does it mean in the stepping? After the exercise yesterday and before, you will see immediately what's the huge difference when you see the visualization. So the excitation, this is another special part for the electromagnetic, the atomic de-excitation. You need to see that when some interactions happen, that leaves actually, when an electron leaves the atom, and the atom remains there in an excited state because there are some holes after the ejection of the electron. This is, for example, in case of photoelectric effect, when the photon is absorbed by the atom, then one electron will be emitted, the photoelectron, and after that there is a vacancy that will be filled. So the photoelectric effect, if you want the complete photoelectric effect going down for the atom to the ground state, it's the photoelectron emission, this part, and after filling the vacancy. And this filling the vacancy, during this process, you can have characteristic X-ray emission or some electrons, for example, Auger electron emission, depending on some conditions. Okay. And this de-excitation is the atomic de-excitation. And of course, there are different details in which you can do this de-excitation. Why? Because in many cases, actually in the high energy physics, these de-excitations are not so important. Why? Because the characteristic X-ray, it's usually in the kilo electron volt, 10 kilo electron volt maximum range. And the Auger electrons are even lower, so they don't go anywhere. So they have so low energy that anyway the high energy experiments are using much higher secondary production cuts for electrons and gammas. Okay, so, but in some other cases, medical applications, this can be important. So there are different levels for the atomic de-excitation. You can control from user interface commands if you want only the fluorescence to set through Auger or the full Auger electron cascade, okay, till the ground state before the initialization of your simulation. You can set these things. We will see a bit more on this in the low energy part, okay, in which constructor you have which settings. But it's important to keep in mind that there is this part. So if you miss some low energy electrons in your simulation, then think about the de-excitation. No energy loss fluctuation. Just briefly, that we were talking about the way in which we describe ionization and Bremsstrahlung. And I mentioned there we saw that, okay, we use secondary production thresholds. So we do not generate secondary electrons that are secondary electrons and gammas. In case of ionization and Bremsstrahlung, that would have an initial energy below a given secondary production threshold that you set as a user. What we do instead is that we take into account this energy that would have been taken by these low energy secondaries from the primary as a continuous energy loss along the step with the mean value, because this restricted stopping power is the mean energy loss. It's important to keep in mind that it's a mean value. Okay, so it's a mean energy loss in unit length. So if you know what was the length, roughly, or I would say more exactly with a bit of approximation, you can say what is the length, and you know what is the energy loss per unit length, so you multiply with the stopping power, restricted stopping power, and you get what is the mean energy loss along the length. It's not as simple, but imagine. But this is just a mean energy loss. You need to take into account that what is the distribution after this mean. You know the mean, and you need to have a model to tell us, okay, this is the mean, but what is the real distribution? And this is what the energy loss fluctuation model gives. Okay, you tell us the mean energy loss, and the fluctuation model will change this mean and will give you something that comes from a distribution randomly. Now, I can tell you, for example, here there is an experiment, no matter which particle, actually, totally unimportant, there is a slab going through the slab. Like we saw in the production threshold, what I show you, an electron goes through a silicon slab. Okay, and we compute the energy deposit in the target. Now, if there is no energy loss fluctuation in this, because this is the energy loss of this particle going through this target. If there is no energy loss fluctuation, what you would see here is a delta function, because you would get only the mean value, because each particle, so the thickness of your target is so small compared to the energy of your primary that practically each primary will go just through, which means that they travel in exactly the same length in your material. So what is the mean energy loss? Length time mean free path, length time stopping power. Stopping power will be exactly the same for each of your primary, so you will get a delta. If you don't believe, I can show. In another case, when 20 keV electron goes through on an aluminium slab with two different thickness, the 320 nanometer and a bit thicker. And this is the energy distribution of the electrons on the other side. So they went through, they lost some energy. And of course, the thicker the aluminum, the more the energy lost. And you can see the experiment and the simulation. It's described very well, taken into account that these are 20 kilo-electron-volt electrons, so very low energy electrons. But it's described very well because there is energy loss fluctuation. If I turn off the energy loss fluctuation, you will get these red things instead of the histograms. So energy loss fluctuation plays an important role if you are applying condensed history simulation. Multi-Percolon scattering, I will get back to this after lunch, together with the models, because it's a big chunk in the electromagnetic description. Multiple scattering is the most complex story. Now, if you would like to get more information on the electromagnetic physics, then there are many ways. So first of all, there is this, in Geant4 there are different working groups. There is an electromagnetic working group that is standard, and there is a low energy electromagnetic working group, you will see in the next section. And you can click here to get to the web page. You will find many things there immediately. In your toolkit, if you go to your extended or advanced examples, you will see many applications already that targeting some electromagnetic simulation and actually use to test and validate some electromagnetic simulations. Of course, we have some validation sites. If you go there, you see many simulations compared with some data. And you can use HyperNews, or if you see some bug, you can report for us in the bug report system. You can click on these blues and you will get there. Any questions regarding the standard electromagnetic part? Good.
Okay, good morning. So this is the third talk of geometry. So you have to change your brain or whatever to come back to something a bit more practical rather than pure physics. Okay. So this is geometry 3. This actually has 3 basically independent topics. The first is magnetic field and other electric field, or whatever you call field. The second is Cad interface. The third is geometry checking and geometry optimization. Okay, basically three different topics. The first is magnetic field. So, if your field is just uniform, we do have G4 uniform magnetic field class. So you just say, here's my field. Don't forget to multiply unit, please, as usual. So this is 1 Tesla along x-axis. That's it, okay? And create a field and set it. to field manager. That's it. It's simple. But if field is not uniform, that is almost always the case. Geant4 doesn't know how to what is your field, so that it's your responsibility to implement field class by yourself. Okay? So my field, the method you have to implement is get field value. Just one method here. Of course, constructor could be. Here, this is the input. As you see, it's not 3-dimensional, but 4-dimensional point as the input. So it is x, y, z, and t. That means even within one event, if particular particle comes here at t equals something, you may return the field value at that point at that time. Okay? So that even within one event, if you have machine gun, so some particle comes later, it may have different field. Okay? That's the point. So this is return value. Should be obviously the 3-dimensional magnetic field. And please note that the point comes in a global coordinate system. Okay? Even if field is quite local, somewhere in the packed region, position always come in a global coordinate system. Okay? That's it. And please here, if you have a rather complicated field map, you should not access to the field map within this method. If it is written on a file, you have to read it in advance. Otherwise, for every step, computer CPU need to access to the file quite often. It's a nightmare. Okay. And also, if you do have some nice, smearing, if you have to calculate quite a lot of exponential kind of things, do it in advance. Don't do it during this method itself. Please pre-calculate. Because this method is basically invoked almost 10 times per step, or 8 times, depending upon which order of Runge-Kutta you use. So this method is one of the most frequently invoked accessed method. Keep it simple. Keep it fast. Okay? So, bit lower, please. Bit. Here. Okay. So one field manager is by default associated with the world volume, and it is set in a transportation manager. So if your field is global, that affects the entire world volume, then, of course, your field or my field, whatever, has to take care of all the geometry, right? But if you believe your field is compound in one particular volume, then you can create local field manager and assign local field to that volume. That is also doable. And this is something you are going to do today at hands-on. The hands-on we are doing since yesterday is a kind of mass analyzer. Okay? So you shoot some particles with some chambers, then there's a field per area, so you bend it, then followed by some other position-sensitive detectors like drift chambers, followed by calorimeter. That means you bend the particle to analyze the momentum, then you measure the energy by calorimeter. By this, of course, you know the mass of the particle. Okay, that is mass analyzer. So we do have a field, but it's a very simplified, naive geometry. So you have just cylinder that represent the field. Okay? So in this case, you set field only to this cylinder. This is something here. Okay? So you'll see this blah blah hands-on today. Okay? Here, what you are doing is you set local field to a local volume. Okay? In this case, if you set this particular parameter flag true, that means or the field propagate down to the daughter volumes. Okay? If something is inside, that volume also see the field. Okay? If this is false, then in this daughter volume, there is no field inside. Okay? So, and please note that some details, but field has to be thread local. Because, for example, the particle you may get in one thread has a different timing from the particle that is in another thread, because you are simulating more than one event simultaneously in a multi-threaded mode. So field has to be thread local. And also, in many cases, in complicated experiments, you need to have a cache mechanism to remember the field value, so that the next step is very close to the previous one. So you may use a cache. But if this cache is used in a multi-threaded mode, if it is not thread safe, it's a nightmare. Okay? So please note your field class has to be thread local. And it's a good starting point, yes. And as I said, B5 is exactly what we are doing for hands-on. Okay? Now, field integration. Okay. So, what we are doing is basically we are solving the equation of motion, or we are actually integrating the right-hand side of equation of motion. There's no magic. And what we use Runge-Kutta, and by default we use fourth order Runge-Kutta. And we also have another class, another level of another Runge-Kutta, second order, sixth order, or even higher, or even helix approximation. So if you believe your field is much smooth or almost not changing, you may want to use some simpler Runge-Kutta. That gives you a bit of performance. Okay? But if their field is so rapidly changing in time position or time, you may also need a bit more complicated, detailed Runge-Kutta. Okay? So what we are doing is the following. Suppose this red smooth curve is a real particle trajectory that is bent by magnetic field. So it has to be a smooth curve. We break it and approximate in these codes that are represented in green dotted line. Okay? And we'll make as many codes as possible to make one step. So in one step, we can take particle from here to there. Okay? And one step may contain more than one code. Okay? In the next here. So here are some volumes. And particles here. You may see particles go in one step from here to there. It's completely the other side of this volume, but it's okay because the real particle actually makes a curve. Okay? So it goes around this volume. It's okay. But we may miss this one. Okay? The particle start from here, making one step to the surface of this green box. Okay? And we miss this one because we don't take this real red curve, but we just use green dotted lines. Okay? So we have a parameter, miss distance. Okay? This is a tunable parameter. So if you really care this corner, you have to set this miss distance small. By default, I think it was 0.7 millimeter or something. Some of that kind of value. But of course, if you make this misdistance small, you have to pay the price. That means we have to have so many small codes, so that we have to integrate fields so often. That is the price, so that it makes program much slower. Okay, and typically, this misdistance should be kind of about the same size as your most small piece in your geometry, or just a fraction of it. Don't make it too small because you just waste performance or computing resources. Okay. And if you cannot clearly see, I'm sorry for the bad choice of the color. And so this is exactly what zoom up of our hands-on. Here the particle blue line comes, here the magnetic field. And if you see just just the ordinary trajectory, it comes from here to there. They make just one step to here and go there. So it, as if it's just a sharp cut, sharp turn, but it's not the case. We really calculate, but smooth curve, and so if you set the step point visible here, it comes this way, and all of a sudden it goes from here to there. But if you use smooth trajectory in Geant4 rather than ordinary trajectory, it remembers all of these codes. So you can see nice, realistic, smooth curve. But of course, it requires more memory. Okay? And even if you do not visualize this way, still we really do the integration. Here. Okay? So we are not cheating anything. But just if you see like this, if there is a strong magnetic field and the particle is looping, if you don't visualize the smooth trajectory, particle may just move from here to there with just straight line instead of nice spiral. It's just visualization matter. So if you visualize these intermediate points, you really see the nice spiral. Okay? That's a demonstration we really do the right physics. Okay? So let me repeat once again that whenever there is no physics interaction, we try to make a step as long as possible. Of course, once a particle comes to the volume boundary, we make a step. But unless there is no volume boundary met, we try to make even several turns. Okay, and so don't be annoyed if you see just straight line from here to there, because we really calculate in this way. Okay? And if you want, you can really visualize as such. So misdistance is a parameter we have already discussed. And also we have few more tunable parameters. That is a kind of miscalculation on the surface or miscalculation on the depth, on how far, there's always a rounding error kind of things. So there are a few parameters, but I don't believe you really need to care about them, except for the first one of the actual misdistance. But this is also, it's very rare you really have to change it. Okay? But here's how to. If you need to change misdistance or delta intersection or delta one step, delta intersection is here, and delta one step is here. Okay? Then here's how to. Okay? And if you have a big field without any granular geometry, you may start to think about, if particle makes so many loops, you may need to think about this misdistance because we have so many integrations. Okay? And actually, if you shoot special particle, what we call charged Geantino, it's a shoot particle, conceptual particle without any physics whatsoever, that it does not lose any energy, but it has charge. It's sensitive to the field. So you can really see if field is well integrated. Okay? If you shoot this particle, given it does not lose its energy, it is supposed to make a full turn and come back to the same position, right? But if you have a lot of granular geometries, because of such a landing errors, it actually always comes slightly inside. Okay? So if you really care this tiny discrepancy, you start to think about this parameter to be tuned. But of course, again, you lose performance. Okay, okay. Any question up to now? It's for magnetic field.
About this chord, how is this related with the step with the control with the radiational method? Is there any relation?
If you have scorer, that means you have scoring meshes, right? So that the typical step length could be shorter because there will be an artificial boundary. But it does not necessarily affect any field integration. We anyway, real boundary or imaginary boundary, up to this boundary we integrate the field. Okay? So if there is no artificial boundary, we may go not to here, but maybe to the other. But anyway, we integrate the field. You may see more steps. Yes, that's it. Yes. Okay, other field. So here, as I said before, by default we use fourth order Runge-Kutta, but we have some others. So you may want to switch amongst these steppers if you need. And for example, Atlas CMS are doing this trick. And inside tracking trackers, they really care the correct integration. But inside calorimeter, they still have magnetic field. Who cares about the electrons in the shower? Could be well integrated? No. So they change steppers. Okay, that makes sense. So here's how to change the stepper. So again, please come to this section if you need to switch steppers. Now, other type of field. Basically, all we need to integrate is this should read equation right-hand side. We are integrating equation of motion. F equal ma. Okay. So whatever the field is, basically all we need is this right-hand side of the equation of motion. So we have electric field, uniform electric field. We have electromagnetic field, and magnetic. What is this? Electromagnetic field. Sorry, this is a typo. So in this case, it's pure electric uniform field. It's how many? 100,000 kilovolt per centimeter. Sounds like it's crazy, but it's really a kind of typical value if you have in a semiconductor. Okay. Anyway, and so create a new equation and set step and so on and so forth. Because the class name, some things are quite lengthy. It looks like complicated, but it's just step by step. Define field, define the equation, set the stepper, and set it the field manager, and so on and so forth. That's it. So there are a few examples for electric field, electromagnetic field. Okay, so just take whatever the examples you need at the start point. And for example, if you need to take care of the very slow, cold neutrons, such neutrons see the gravitational field. Actually, it drops. Okay, if this is the case, yes, you just create a new equation of motion that takes care of the gravity. Okay, that's it. Then we can integrate it. Although we don't have gravity field here by default, but you can do it. Question? Okay, the Cad interface and GDML. First of all, GDML. GDML is abbreviation of Geometry Definition Modeling Language, or something like that. And according to GDML developers, I don't believe it, but at least they said, anyway, GDML is XML based, so according to them, it's easy to read or it's easy to whatever, if you like. And so, for example, here, this constant name is length, value is 2.65, and variable name x, and current value is 6, and so on and so forth. Here's the rotation matrix, or here is position, or rotation, and so on and so forth. So basically, it's another way of writing numbers instead of C++. Basically the same. Okay? So, simple element, material, so on and so forth, which Dennis described yesterday, how to define material. Okay? It's the same way. And for solid, we have these different kind of shapes. Okay? So for box and union or whatever, you can do that, and you can read it. Okay? The world volume made of air. Okay? So if once you have GDML file, you may want to read it. Okay? So here we have Geant4 GDML parser. You include this header file. Then in the detector construct method, here's the parser object, and just parser read method with the GDML file. Then you ask to the parser, get world volume. You'll get the pointer to the world physical volume. You are done. Okay? Of course, given this GDML file is okay. Okay, that's it. And also, you can export your geometry to GDML. So, if you like, you can write GDML. And to use GDML, we depend upon the external library, the exact C parser. Okay? So, if you want to use it, you have to download and install it before you actually compile Geant4 library. And in the CMake, you have to say you use GDML. Then CMake will search the installation of this parser and include the library. Okay? And we have a few examples here. So if you are interested in, just check it out. Okay? And for example, CMS has a full description of its geometry in GDML. Atlas has not yet succeeded to make the full GDML because it's too huge, too detailed, in other words. I don't know if Alice has it. I don't know. LHCb has it, yes. So that is GDML. Now, CAD. And there are a lot of requirements. We are quite aware of it to import CAD geometry into Geant4. Okay? There are a few ways. None of them are complete yet. Okay? But first of all, one of the biggest problems is typical CAD format does not have any concept of material. That's the biggest problem of us. We need material. So anyway, so the best one we have, not we ourselves, but we find is this CAD mesh. It basically takes STL or PLY format, and it spits out basically tessellated solid of Geant4. It's very powerful, yes. So, please. Oops. And the other, sorry, I don't know why, but order is wrong. So CAD mesh. This was developed by Australian medical physicists, so that you see not only the simple shape, but some shapes which non-medical people never use. Okay, here's bone, hip, whatever, and this one is multi-leaf collimator for the treatment, and so on and so forth. This is flattening filter. This is also for gamma therapy things. But anyway, so it takes STL and PLY, and it creates G4 tessellated solid. You can download code for free, and you can. And once you use it, please refer to his paper so that he'll be pleased. Okay. And this is Dragon. That is one of the Stanford mascot. So he's one solid. Next time I can shoot gamma ray or something from his mouth. Okay, and the other is Stanford Armadillo. Yes, it's one solid. So given it's a solid, you can use it and take it to your logical volume. You may say this is made of whatever. Okay. And also, good part is, given this is a solid, you can create a logical volume and physical volume. You can press it, okay, within your geometry. Okay, GDML cannot do it very easily, but in this case, you just get it as a solid. Okay, but the problem is there's one rather serious problem here. It converts whatever the CAD geometry into tessellated solid. Tessellated solid is something, as I said, it has facets, plane of triangle or square. With a lot of facets, it approximates the shape. So if you have curved surface, there will be a lot of approximations. So if this curved surface is touching to yet another curved surface, there may be a problem. Because of such approximation, there could be a gap, or there could be overlap. So be careful. Just putting Dragon or Armadillo in the open box, you're okay. Okay. But if you have to make two volumes touching to each other, and they have curved surface, you have to be careful. Okay. So here's how to CAD mesh included, and load mesh. So this is the physical volume, right? So logical volume. So this is G. Okay, sorry. So this is a CAD mesh, read a file type, and you get a solid. That's the point. Okay, you can use this solid to create a logical volume with material and press it. Okay, that's the point. So let me come back to the other ones. Oh, sorry, where was that? I don't know, but slides are shuffled. Another two CAD interfaces, so-called ST Viewer and FastRad. And none of them are free. You have to pay, except for the FastRad. If you limit yourself to 5 volumes or something, it's free. But if you have more than 5 volumes, you have to pay. Okay? It originally funded by European Space Agency for free, so that it was free, but then they are commercialized. So none of them are complete. There are time to time some mistranslation. So I invite you to this particular publication that discusses a lot about how you import CAD geometry into Geant4. Okay? If you have a volume per shape, this CAD mesh is the best option. But if you have a big CAD drawing of all the components in, you have to buy ST Viewer or FastRad and do conversions. And if you're lucky, everything goes well. But still, none of them take care of material. So you have to really set material by hand for each of the volumes. And we used to have CAD interface by ourselves. It was written by an engineer somewhere in the company in US. but he wrote it in C, old style C, so it's no longer compatible with C++. So we cannot compile it anymore, so we dropped it. So if we have someone, computer engineer or someone, who is fluent to old C and new C++, he can convert it, then we can recover it. It's a nice summer job, maybe. So that's it. Any question about CAD? One more thing. Yeah, this Attila is developed by a company called Variant. Now they spawned to a new company by themselves. But anyway, the good part is, in this case, this program is clever enough so that if there's a shared surface, they take that part shared, so that there is no issue of overlapping. It's good, So we can use this to whatever does shapes, but this is expensive, as you can imagine. Yes. So any question to CAD interface? Okay, with another 5 to let's say 5 minutes or 10, I go for the last topic in this talk, geometry checking. So, as I said several times, we don't allow overlaps. In this case, this purple circle and this red trapezoid are overlapping to each other. It's not allowed. And in addition, this purple guy is protruding. Protruding means part of it is outside of its mother. It's not allowed. Okay? So, they are not allowed. The problem is how you detect it. Okay? And there's no one solution to detect all the mistakes. Okay? And the typical symptom of once you make a mistake is that particle may ignore one volume, because if particle comes from here, from this side, particle navigator believes first volume encounter should be this mother, but particles already come here, and so it cannot detect this red point. Then it comes here. It's already inside A, but navigator believes it's still in the mother volume. Then you will not see this purple square. Or whatever nasty thing could happen. So there's no particular typical symptom. But some symptoms are volumes are ignored, or particle may disappear from one point and show up again completely the other side of the detector without any material, whatever. Or anything strange happen. Or tracking becomes ultra slow. So if you believe something goes wrong, you have this kind of problem, okay, most likely. And there are a few tools we offer to detect this kind of mistakes. The first one is this parameter flag, Boolean flag. When we discussed yesterday about PV placement, I postponed discussion about this parameter. Okay. Once you set this flag on, or true actually, what we do is let's come back to here. So, suppose we are discussing about this volume B red. We randomly generate by default 1,000 point on the surface of this volume B and check if this volume could be inside purple or any other volumes. If that is the case, we are having overlap, right? And also checking if any of these points are outside of mother, then there's a protrude, okay? So we do this. So we invite you to, once you complete your geometry, we invite you to try this once. And if there's a problem, there's a report, you see, okay? But also please remember to put it back to false. Otherwise, creating whatever 1,000 point randomly on the surface for each volume is quite costly. Okay, so you should do it only once. Of course, if you have problem, fix it and then do it once and you are done. Okay, and also given it's for placement volume, if you identify track does nasty thing at particular volume, or particular, let's say this purple, then you may say this flag true only for that particular purple. You can do it. Okay, and this flag is available only for two kind of shapes, placement. One is this placement. The other is parameterized volume. Because for the case of parameterized volume, parameterized data could be by mistake overlap. So we can do it. But you don't see this parameter flag for replica, for example, because for the case of replica, we know we are slicing. There cannot be any chance of overlap itself. Okay? So try this once. If you don't see any error message, you're okay. Okay? And other tool is online tools. We shoot Geant4 head-to-head, okay, and see if volume boundaries found are in a completely opposite order. If that is not the case, most likely we are having this kind of trouble. But in this case, it's not easy to shoot on any direction. So it's not perfect, but it still works. And if there's a problem, you see this kind of report. Now, dawn. If you use dawn visualizer, instead of dawn, you may use David. David is the same visualizer derived from dawn, but it really highlights if something is wrong. So it visualizes in red if there is any volume overlap. Okay? It is not perfect, but time to time it really visualizes where is wrong, the issue. Okay? So David can be downloaded the same directory as dawn. Okay. Okay. Question? Yes.
When you do the last parameter replacement.
Yes.
So you have to do that for which one? All
One after the other, maybe. Or actually, you can set true to order placement if you want, but it's ultra slow. But if you have any suspicious volume, you set it only for that one. Yeah. Yes. Okay. Just to finish up, let me explain what we do for geometry optimization. It's a new trick we introduced at Geant4. It's unique to Geant4. So, suppose this is the mother volume. It has some smaller granular things inside, data volumes. So when you type run bmon, for each mother volume individually, we slice conceptually, make slices to make each slice that should contain only one daughter. Okay? The idea is that suppose there is no such a slice, particle is like here. We have to check if this particle may hit to any of these boundaries, daughters. Okay? We have to check everything. But if we have such a slice, we are certain there is only one daughter inside. So we just check to it. Okay? And if there's such a slice, these slices, there's no daughter inside, we merge so that we don't have any unnecessary memory waste. But anyway, we do it this way. Okay? We call it smart voxelization. And if one particular direction is not enough, we try the second axis and third axis if necessary. Okay? Try to make each voxel, a slice of voxel, contain only one daughter inside. Okay? That is what we do. So you may recall in a parameterized volume, there was a suggestion which axis the repetition dominates. navigator will take that your suggestion to start, for example, in X to slicing in along the axis you suggest. Okay? If you say your parameterized volume repetition dominates in along x-axis, we start slicing in X, and so on and so forth. Okay? And if you say unknown, that was an option. We, since the beginning, try to make three-dimensional slice. That is quite costly in memory. Okay? And if you set run verbose greater than 1, let's say 2, you get this kind of report. That is, for each individual logical volume, it says how much of the CPU time in percent used, or how much of memory was required, so on and so forth, per individual logical volume. Okay? Because this voxelization is done for each logical volume. Okay? And so if you find one particular logical volume that dominates in memory or CPU time or whatever, that mother volume has two complex daughter volumes, and it eats up all the memory and performance. This actually happened to CMS. Originally they needed to close the geometry. It took more than 40 minutes. When you type BMON, it took 40 minutes. You have to just wait for nothing. And after 40 minutes, it starts tracking. And it used a huge amount of memory. It happened only for one mother volume. That was the mother volume of the silicon detector. They put whatever the complete geometry, quite detailed, quite granular, in one mother volume. So voxelization took forever. Okay? This may happen. So if you believe after you type BMON and it takes so many times, you encounter this issue. So just try this and see which volume causes problem. And then also you can visualize. And here's a parameter for logical volume. Get smartlessness. Set smartlessness, make it a bit more stupid. That means it's a parameter. How many daughter volume is allowed in the slice? By default, it is 1. Okay? So that each slice, we should have only one daughter. But if you set this to, let's say, 10, each slice may have 10 daughters inside. So that voxelization could be much simpler. And actually, that is what CMS did. And from 40 minutes, now the initialization takes only 7 seconds. The huge difference. But of course, you have to pay penalty. For each tracking time, each particle, instead of one daughter, we have to check 10 daughters. So it's a trade-off. Okay? That is something you may want to remember. Okay, that's it. Question?
Yes, I have a general question.
Mm-hmm.
You showed how to get geometry from several different systems. Is it possible that we could, for example, someone or some experiment has a previous geometry made in Geant3 that we can import?
Yeah, there is Geant3 to Geant4 converter. We have it, and it is still maintained, I believe.
It's one of the extended examples.
Yes, there's G3 to G4. Okay. Yeah, we have that too. We can import Geant3 geometry to Geant4. And also, there's a way to combine or make granular components of GDML, so that if you run somehow in the part of your geometry in Geant4, you spit it out in GDML, you can merge it into another GDML file. That works. Yes. Okay. Let's have 15 minutes break then. So we start at 5 minutes before 11.